Okay, so in this lecture, let's start with the discussion of lattices. Lattice. Okay, so in the previous lecture, we had discussed about a free abelian group of rank n, and that is the tool which we will be requiring here. Though we won't be requiring, the its importance as a group, rather we will be requiring the structure it follows and the concept of the basis it acquires. Okay, so the geometrical intuition will be very easily visualized. There's nothing too difficult in that. So you just need to have a sense of how the basis spans a certain vector space. Okay. So let us start. So let E1, E2 till Em be linearly independent vectors in Rn. Okay. So I am not claiming that m equals n. I am collecting any arbitrary collection of arbitrary number of linearly independent vectors from Rn. Then the additive subgroup which is clearly abelian, because we are talking about additive subgroup of Rn, considering Rn as the additive abelian group, generated by these vectors E1, E2 till Em is called a lattice of dimension n. Clear? Immediate things to observe here, or rather I can also add it up here, is called a lattice of dimension n generated by E1, E2 till Em. Okay, so the immediate observations which we can carry out from here is that these elements, that these E1, E2 till Em, we know that these elements are linearly independent over R, right? Because Rn is a vector space over R. So this immediately implies that they are linearly independent over Z as well. So these are linearly independent over Z as well. And so if they are linearly independent over Z, and we are considering that subgroup, that additive subgroup which is generated by these elements, so elements of that additive subgroup are just Z linear combinations of these elements, and these elements are linearly independent over Z. So this immediately gives out the fact that this lattice is a free abelian group of rank m, right, because it has a m number of elements in its Z basis. Clear? Okay. The geometric picture of this, as I said in the first portions of the first lecture. So as an example, let us simply consider, let's say R2, just consider R2, and we consider the standard ordered basis. Let's say consider the standard ordered basis, which simply consists of the vectors 1 0 and 0 1. So what we actually want to see is that we want to see the space, or rather in this case for now let's say the group, which is let me use the standard way of the standard notation for showing generators. So which is generated by the elements 1 0 and 0 1. Sorry, in other words, which is just the collection of the elements of the form a1 times 1 0 plus a2 times 0 1, where these ai's are simply coming from Z. Okay, so how can we simply picturize this out? So suppose this is your R2, and let me give some grids here. So suppose this is 1, this is 2, this is 3, and this is 4. This is 1, 2, and 3, let's say. Then I have here -1, -2, and -3, and I have here -1, here -2, here -3, and here -4, right? Okay. Now so let us start with the vectors which we originally have. So I have the vectors 1 0, and I have the vectors 0 1. Now if I add these two vectors, that is if I keep a1 and a2 to be just 1, then I'll eventually get the vector 1 1. So that will be a vector here, right? So this is one vector. If I take a1 and a2 both to be 0, I'll get the origin. Now suppose I choose a1 to be say -1 and a2 to be 1, then I'll get the vector -1 1. So so the x coordinate will be -1 and the y coordinate is 1. So this will be a vector here, right? On a similar note, I can actually just cover up this whole space with these dots, considering all possible linear combinations. For example, if I choose a1 to be 4 and a2 to be 3, then I'll get the point 4 3 here, right? And on a similar note, I can just grid out these elements in this way, right? I can just grid out these elements. So these grids, they constitute, I mean these dots, you can think of these dots, they constitute what we typically are calling the lattice. If I change the basis in this case, then we'll get we might get a different a different arrangement of these lattice points. Yeah, we can call these dots to be lattice points as well. Okay, so try using a different vector and try to figure out how this lattice point, what this lattice point looks like. Okay, and check whether they actually are equal to the lattice point with respect to this standard basis or not. So now our intention is to topologize the lattice, because since we are actually talking about a geometric notion and we are working inside vector spaces, we know that inside vector spaces I can define a function which we usually called a norm. Students who have studied functional analysis, they are pretty much acquainted to this fact that we can talk about the, or we can generalize the notions of distances. Then we can distances, and I can also the magnitude of vectors, magnitude and orthogonality of standard R2 or R3 vectors, that is the 2-dimensional or 3-dimensional vectors in cases of finite dimensional or infinite dimensional vector spaces, using the notions of norms. Norms are usually used to to talk about on a basic note, to talk about the magnitude of vectors, or rather we can say that to be distance of a vector from origin, and these norms sort of induce the concept of the metric function, which actually generalizes the concept of distance between two vectors. And the orthogonality concept, in fact the orthogonality is not immediately a generalization. We actually wanted to generalize the concept of angle between two vectors, but an arbitrary angle between two vectors is in a conceptually very complicated to generalize. But the more useful case is when two vectors are perpendicular to each other. In that case, we know that their cross product or what we call their dot product. I'm exactly sorry, I have used the term cross product. Sorry, the dot product or what we call the scalar product becomes 0, right, when two vectors are perpendicular to each other. And when two vectors are perpendicular to each other, we call those vectors to be orthogonal to each other. So we can in fact generalize this notion of orthogonality of two vectors in terms of what we call inner products, right. So these are standard topics from topology. In fact, a bit further from topology, these are standard topics from the concept which we call functional analysis or the study of normed linear spaces. So now the concept of lattice, it precisely lies inside the n dimensional Euclidean space, right. So in fact the definition immediately, so a lattice is inside the n dimensional Euclidean space. And if you have studied advanced real analysis or the concept of metric spaces or the concept of topological spaces, then we know that a n dimensional Euclidean space is a well defined metric space, right. What do I mean by metric space? So arbitrarily a metric space is a certain vector space or a certain topological space where we have the generalized notion of distance between two vectors. Okay, so it's a well defined Euclidean space. More can we say that it's a well defined norm linear space as well. We can define a well defined norm over these vectors, and these are some sort of the most useful spaces which we eventually study, because all sorts of generalizations of vectors which we mentioned are all valid or all can be well defined in a n dimensional Euclidean space. So it's a sort of it's sort of intuitive to apply some sort of topology to lattices. Okay. So let Rn be equipped with its standard metric, So what do we typically mean by its standard metric? This is sort of a generalization of the distance between two vectors which we usually study in the concepts of vectors in our school level. So if you quickly recall that if I have two vectors, say x1 y1 and x2 y2, then the distance between them I can refer to it as, so suppose I write this as say A and I write this as B. We use this notion or rather this symbol d of AB, which means the distance between A and B, and we usually write this as x1 minus x2 squared plus y1 minus y2 squared. So in fact this can be generalized to an n dimensional Euclidean space. So if I have d of xy, so I can write this as the square root of x1 minus y1 whole squared plus x2 minus y2 whole squared and so on till xn minus yn whole squared, where this x is the n tuple x1 x2 till xn and y is the n tuple y1 y2 till yn. Now if we talk about this definition in terms of a norm, so as I said that norms are basically giving up the they are basically generalization of distance of vectors from origin. So if I choose this x itself, I can define the norm of this as simply the distance of it with 0, and that will eventually come out to be x1 squared plus x2 squared and so on till xn squared. So this is called the standard norm over Rn, and this is called the standard norm over standard distance, standard metric over Rn. In fact, if we have a well defined norm, then this distance between x and y, this can be simply talked with the norm of x minus y. Clear? Okay. So now what we start with is that we say that Rn is equipped with its usual metric or its standard metric. Now when Rn has its okay, let me not mention it anymore. define the closed ball of radius r and center x as brx. Okay. The other notations which we, so I shouldn't use the term define, in fact I should use the term denote. The other usual notations which we usually have, so these are the standard notations. We also write it bxr, and it is certainly the elements a in Rn, such that the distance between a and x is less than r. And if I talk about the closure of this, so this is generally called the open ball of radius r centered at x. If I take the closure of this, then this will simply come out to be the elements such that its distance is less than or equal to r. So in a way, what we are basically doing is that this closed ball with a center x and radius r, this is nothing but the union of the open ball with center x and radius r, union the boundary of it. Okay. Okay. These are very standard definitions if you have taken a course in metric spaces, but rather let's talk about a quick visualization. Suppose we are in R2. In R2, let x be simply the point, the origin, let's say, and let r be 2, or let's say r be 1. Then by the definition, or let us first talk about in this way. So we have x is equals to 0. Let me consider this a. Okay. So by definition, the open ball with center at a and radius r, which is nothing but b01. So this is the collection of all the elements xy in R to such that the distance between x and y, that is a norm of xy minus 0 comma 0, I am not writing that anymore, this should be less than equals to 1. But if you carefully observe that this is this norm is nothing but by the standard definition, so it is just root over of x squared plus y squared is less than equals to 1, less than 1. Now a quick recall from your school level maths, that if you have x squared plus y squared is equals to r squared, this necessarily defines a circle, of radius r centered at a, centered at 0. So if we have this to be less than or equals to r square, then this will define if the whole region inside the circle, leaving the exact circle, right. So ideally in this case, this b01 will simply look like, so suppose I have r2 here, so this is r2, and say this is the point 1, this is the point 1, this is minus 1, and this is minus 1 as well. So this essentially defines the, wait a second, I guess this will do, okay. So this necessarily defines the unit circle, but not the exactly not the unit circle. Wait a sec, yeah, so let it be like this, yeah, I guess this will do, okay. Okay, so now if I choose any point on this circle here, then the distance from origin of this point will be exactly 1. I don't want points which have distance from origin exactly 1, but I want those points which have distance from origin less than 1. So it will constitute the whole of this inside, but not the boundary, leaving this. This is what we call an open disk. Okay, this is what we call an open disk, and this boundary, which is the circle, this is exactly the boundary of B. So if I involve both of these, I get the whole circle along with everything inside, which is what we typically call the closed disk. And you can think of this definition of a closed ball to be just a generalization of this closed disk. Okay. whatever. So we have set the notation for the closed disk to be B R X, right. Now there comes a definition which is also elementary in case of metric spaces, that a space from Rn is said to be bounded if and only if, or rather it will just do from a one sided implication, if it is completely contained in a closed ball of radius r centered at origin, with r being obviously greater than 0. Okay. So visually you might think of it in this way, that suppose this is your R2 and this is an arbitrary closed ball. So this is an arbitrary closed ball, this is BR0 centered at origin and with radius r. Wait a sec, let me just fix it. Okay, with radius r, and this space x is somewhere inside. So suppose this is your x. Okay, I can think of it in this way. Clear? Okay. So in this case we say that x is bounded, and the notion which you can immediately carry out from here, that whenever you choose any vector out from x, the distance of that vector from origin must be less than r, right, less than or equal to r. So if the norm of every vector from x is less than or equals to r, then it is clear that the complete set of all these vectors, it resides inside the closed ball, and then we are good to go. The next definition is what is important in our case, which we will be dealing with throughout the end of this lecture, is that we say a subspace of n x is discrete if and only if that space intersects with the closed ball of radius r centered at origin at finitely many points. So this is a finite set. This is a finite set. Clear? Okay. Now let's come back to the first diagram of lattice we made. Yeah. If you carefully observe that I can have multiple points here, but the thing to observe is that whenever I choose any circle centered at origin, I think this circle was pretty good. Yeah. So whenever I choose any circle centered at origin, this lattice, the whole lattice, all these points constitute the whole lattice. The lattice intersects the closed ball centered at origin of radius r only at finitely many points. So in this case you can see that we are a 1, 2, 3, 4 and 5. There can be much more number of these points, but the number of points will surely be finite, which is clearly observable out from here in this case. And that immediately, and you can also see that if you just increase the radius of the circle, this finite intersection still remains, and if you shrink it down, it's also hold in that case as well. So this brings us to the next immediate theorem, which is the most important theorem of this lecture, that an additive subgroup of Rn is a lattice if and only if, so it is a two-sided implication, it is discrete. Okay. So it is a lattice if and only if it is discrete. So in order to talk about lattices, it will be enough to talk about those topological subspaces of Rn which, or those vector subspaces, it will be better to talk about vector subspaces, those vector subspaces of Rn which intersect the closed ball of radius r centered at 0 only at finitely many points. Okay. So let us talk about the proof of this, and the proof is a bit complicated, but you need to work through these steps to get a view of what's being done. Proof. So we are working in Rn. So suppose L is a lattice. Suppose L is a lattice generated. Okay. Suppose L is a lattice generated by the vectors E1, E2 till En. Okay. Now it suffices to consider, or you can, it's or rather I should use it in this way, we can consider M to be equal to N for the proof. And how I can I do that? Because suppose I am in Rm and I am talking about a lattice of rank n, or I am talking about lattice of rank n. Now topologically Rn is a subspace of Rm whenever n is less than or equals to m. Okay. So I can just shrink Rm down to Rn and work out the proof in Rn. Since the whole proof is still contained inside Rn, which is in fact contained inside Rm, the proof holds in the larger space as well. So it suffices to just choose M to be equal to N, or rather it is enough to choose that this lattice is of rank N, which is equals to the dimension of the Euclidean space which we are working on. Okay. So that so therefore we can assume L to be of dimension. Okay. Now since E1, E2 till Em these generate L, then by definition these are linearly independent vectors. So E1, E2 till Em, sorry, now I am using N in terms of M. So these are or rather I can say that these form a basis of Rn, form a basis of Rn. Clear? Therefore every vector from Rn, every V in Rn can be expressed as so I can express V as lambda 1 E1 and so on. I can continue till lambda n En. Okay. Okay. Now observe that define a function f from Rn to Rn, and how do we define that function? Such that f takes an element which is an arbitrary linear combination of these Ens and it just sends it to the coordinate vector lambda 1 till lambda n. Okay. To be mentioned that in this case we are talking about vectors in Rn, so these lambda i's come from R. Okay. Clear? Now we claim that the image of the closed ball centered at the origin with radius r is bounded. Okay. And let or rather it be bounded. That will be enough to talk about for now. Why is it true? So I'll just give a scratch of why this is happening. See, when we are talking about finite dimensional vector spaces, there is the concept of a change of basis. That's quite a complicated thing to talk about in a short span of time, but I'll surely refer you to any basic book on linear algebra. You can see about this in Friedberg, or you can see about this in Hoffman-Kunz. So how does this change of basis works? Okay, so let me be a bit brief. So let V be an element from BR0, then the norm of V is by definition less than or equals to R. Consider FV to be P times V, where P is the change of basis matrix, is the change of basis matrix, and V is the coordinate matrix, is the coordinate matrix of V in terms of the standard ordered basis, in terms of the standard ordered basis. Clear? Okay. Because see, we are sending f, we are sending through this function f, we are sending each vector to its coordinate matrix, coordinate form, and the basis we have assumed that's an arbitrary basis. We have not assumed that to be just simply the standard order basis. If we have assumed the basis to be standard order basis, then this P would just be the identity matrix. Since we are talking about an arbitrary basis, and V, see here V is just a vector. It is a vector considering the coordinates. So if like these things we have discussed in the previous lecture, how a coordinate vector looks like. So V is just the coordinate vector, because when we will be talking about standard ordered basis, then the vector will just constitute the each component of it in the vector form, or of it in the n tuple form. So and P constitutes the standard ordered basis, which transforms the coordinate vector of V in terms of the standard ordered basis to the coordinate vector of V in terms of the some arbitrary basis which we are talking about. Okay. Now P is a matrix, and we know that matrices are equivalent to two linear operators over a finite dimensional normed linear space, which implies that P is a bounded operator. P is a bounded operator. So this implies that the norm of P is less than or equals to C for some C greater than 0. Okay. So this is often called the operator norm. Okay, these are topics from functional analysis. If you have taken a course on it, then this part will be clear to you. Otherwise, you can just take it to be take it to be a fact that the image of the closed ball of radius or center at 0 is bounded. Okay, so yeah, so this happens, but therefore the norm of Fv, which is just the norm of P times V, so this should be less than or equals to C times the norm of V, which is less than or equals to C times R. So I can just assume this to be K, and so this simply speaks that f of V is bounded, because if the norm of f of V is less than or equals to K for every V coming from B 0 R, so that implies that the space of these images, the space of the images of every vector coming from B 0 R is some closed ball of radius K centered at origin. In other words, it is bounded. So let norm of f of V be less than or equals to K for all V in B 0 R. Clear? Because it is bounded, I can assume a bound of it, because it surely exists. Now let I is equals to 1 to n be an element from the closed ball with each ai coming from Z. So I am choosing an arbitrary element from the lattice which is in the intersection of it and the closed ball centered at origin of radius R. But for this to happen, I must have the norm of this to be less than or equal to R, right? Sorry, less than or equals to K, right? Sorry, I should use not, I don't want to use this. A1, A2 till AN. Now see, this is the image of the summation AI EI under F. So this must be So this is an element from B0R, so this must be less than or equals to k. It comes out from here. Okay. But if the distance of the whole vector coming out from the origin is less than or equals to k, that means the distance of each individual component, each individual real component of this vector is also, sorry, each individual integer component of this vector must also be less than or equals to k for all I. But the thing to observe here is that k is some finite real number, and each of these ai's are integers. So the norm is typically a non-negative integer. So this is less than or equals to k, right? What I actually wanna speak out here is that this is a this gives a finite number of solutions. This gives only a finite number of solutions, because see, this means that ai is less than or equals to k and greater than or equals to minus k, and we will always get a finite number of integers which is bounded from both sides, right? So this has only finite number of solutions. But if this is the only finite number of solutions, so there are only a finite number of possible elements from the lattice which can be inside the closed ball. In fact, this immediately means that L intersection BR0 is just finite, which means that L is discrete. Clear? Okay. Okay. Now let's talk about the converse part. So conversely, this part is a little bit complicated, but rather let's talk about. So let G be a discrete subgroup of Rn. Okay. What we actually want to show is that, so let me just write it point wise. So to show G is a lattice, but to show that G is a lattice, I need to show that G is generated by some collection of linearly independent elements from Rn. Okay, this is what I actually need to show. So I actually need to construct a collection of elements which will generate G and are linearly independent. Okay, that will do the job. So let's see how we can do it. So we prove by induction on n, let's say. Okay, clear? Now suppose, so we actually will be showing that L is a lattice of rank n, dimension n. So suppose G1 till Gm is a maximal linearly independent subset of G. Let V be the subspace which is spanned by the elements G1 till Gm minus 1, and then consider G0 to be G intersection V. Okay. Then observe that this implies that G0 is discrete, because G is discrete, right? But if G0 is discrete, then by our induction assumption G is a lattice. G is a lattice, but if G is a lattice, then this implies that there exists linearly independent elements H1, H2 till say Hm, which generates G0, But see, V is a vector subspace which is spanned by the elements G1 till Gm minus 1, and G1 till Gm minus 1 is linearly independent because G1 till Gm is linearly independent, right? we know that the subset of a linearly independent set is still linearly independent, right? So but since these elements g1 till gm minus 1, these are in g naught, and v and g is also g is also contained inside v, which is a span of these elements g1 till gm minus 1. So what are we typically observing here is that g, every element of g is some linear combination of these elements g1 till gm minus 1. Moreover, these elements g1 till gm minus 1 are linearly independent, so it must constitute the basis of it, right? Therefore, if it constitutes the basis of, we know the number of elements in a basis is unique, so therefore m prime, or rather I just use the word m, right? So m is nothing but, I guess I have already used the letter m, so I should use m prime here. That means m prime is just m minus 1, and the collection h1 till hm minus 1 can be equivalently replaced by the collection g1 till gm minus 1. Okay. Thus every element of g naught is a z linear combination of these elements. So therefore every element of g naught is a z linear combination of the elements g1 till gm minus 1. Okay. Now let T be a subset of G. Okay, so let T be a subset of G which contains all the elements x of the form a1 g1 and so on till am gm, such that each of these AIs come from R, and these AIs are in the interval close 0 open 1, with am only having the freedom to be equal to 1. Okay. So we are considering a section of this discrete subgroup G which is sort of bounded inside a rectangle, if you carefully observe this. Okay. This will be precisely of use. Okay. So as I said, this is some sort of bounded inside a rectangle, so this implies that T is bounded, because if it is sort of bounded inside a parallelogram, or it is bounded inside a rectangle geometrically, then it is bounded inside some closed ball centered at origin. Or in fact, if you check out just the norm of x, then the norm of x will be clearly interpreted in terms of the norm of these AIs, and norm of each individual AI is between 0 and 1, or it can be just thought of to be less than or equals to 1. So I can think of a closed ball immediately, right? So T is bounded, but since G is discrete, so G has only a finite intersection with any closed ball. This implies T is discrete as well. Sorry, I should say T is finite, which implies T is finite, because T lies completely inside a closed ball, right? T lies completely inside a closed ball, and the intersection of elements from G with the closed ball is finite, and since so T is precisely inside the intersection because it is completely inside the closed ball, so it must be finite, right? So now let x prime be an element from T. So since it is finite, we can talk about a greatest coefficient and the smallest coefficient equivalently, because there are only a possible a finite number of possibilities for these coefficients of the elements in T, because the basis elements are fixed. So let x prime be in be T with the smallest non-zero coefficient am. Okay. So the am coefficient is smallest in case of x prime, and say x prime can be written as b1 g1 till bm gm. So whichever coefficient is am, whatever it be, it is the smallest, and so we sort of give a certain representation of x prime in terms of gm's. The thing to observe here is that certainly the collection g1 g2 till gm minus 1 and x prime is linearly independent, and this immediately follows. So this is something which you can check immediately. Take any non-trivial combination of these elements, you will eventually find it. Why is it linearly independent? You will find it immediately whenever you take a non-trivial combination, linear combination of these elements. So this follows from the fact that the vectors g1 till gm is linearly independent, and this was our assumption. Okay, now so our claim is to show that this is in fact something this set in fact spans G. So now let small g be an element from capital G. Consider integer coefficients which we can efficiently do Ci such that G prime, a vector G prime, which can be written as G minus Cm times x prime minus C1 G1 minus C2 G2 so on till Cm minus 1 which is less than or equal minus Cm minus 1 Gm minus 1, this vector is in T. And why can I do that? Because so these so see, I am choosing G to be an element from capital G, right? So I have no restrictions of the coefficients of any vector represent any linear combination representation of G to be inside the integers. But what I can actually do is that whatever linear combinatorial representation of the vector G is, I can simply scale those coefficients down to a real number between 0 and 1 by just removing out the integer portions. What we are typically doing here is that suppose I have an element 2.10, I can just cancel out the integer portion and I can bring it out to 0.10, which is less than or equals to 1, or in fact less than 1. And this is exactly what I am trying to do, because the elements in T are having coefficients less than 1, less than or equals to 1, and that is the exact thing which I am trying to do, that I am just cancelling out appropriate coefficients from the linear combinatorial representation of G in terms of the elements we have, to bring it down to an element inside T. A thing to observe here is that sorry, I was using the blue pen, right? And the coefficient, so this is a further restriction, the coefficient of Gm in G prime is less than Bm, but non-negative. Okay, but by the choice of x prime, this coefficient must be 0, because we had chosen x prime to be a vector in T such that the leading coefficient, that is the coefficient of Gm, must be the smallest, right? But here we are seeing that the coefficient of Gm is less than Bm. Bm was the smallest possible choice for the coefficient of Gm. We are getting a different vector G prime which is having a smaller coefficient of Gm, but in that case this coefficient coefficient must be equal to 0. Okay, which will imply that G naught is in G prime is in G naught, right? Because then we are basically bringing it down to a span of the vectors G1 till Gm minus 1. But then this immediately speaks that this implies that x prime and all the other vectors G1 till Gm minus 1, these generates G, and hence G is a lattice, right? Hence G is a lattice, because from here I am able to represent G in terms of a linear combination of the elements x prime G1 till Gm minus 1. Clear? Okay. Now this collection T which we talked about has a fine name, and it's quite an useful thing to talk about. So if L is a lattice generated by E1, E2 till En, we define the fundamental domain T, or this is also sometimes called the fundamental parallelopiped. I guess parallel word contains only one R. Parallelopiped to be the collection of all elements AIEI, where these AIs come from R, to be noted, for which 0 less than equals to AI less than 1. So, so if I go back to the description of the lattice we had previously here, so let me just remove the circle for now. So see, I can actually talk about this being this part. Okay, I am not considering the boundary, I am considering only the inside. Okay, this region. This will give me the fundamental parallelopiped or the fundamental domain T. This I can refer to as T. Clear? Okay. Got it. And we have a lemma here that each element of Rn lies in exactly one of the sets T plus L for this L coming out from the lattice. So this means that if I take the fundamental domain, and I translate it by some element from the lattice, then I will eventually cover the whole of the Rn. That is exactly what we are talking about in this case. Okay. So let us quickly talk about a proof of it. So let us see a proof of it. So what we will be proving is basically that whenever I choose out an arbitrary element from Rn to show that for all W in Rn, W can be written as T plus V, such that T comes out from capital T and V comes out from L. Okay. So T is the fundamental domain from L. So how do I prove this? So let's see. So let V1 till Vn be a basis of L, which gives the fundamental domain T. If you can obviously observe that, so the first exercise which I gave, that choose a different basis and plot out the lattice represented by that basis, you will see that whenever you change the basis, the fundamental domain will immediately change. Okay. So that is also an observation which you can account for on your own. So we choose a basis as that the fundamental domain is our required T. Okay. So now since now clearly these elements V1 till Vn form a basis of Rn, because they are n in number and they are linearly independent by choosing them to be a basis of L. Therefore, whenever I choose out an element W from Rn, I can write this as some linear combination of these vectors V1 till Vn, alpha n till Vn, such that these alpha i's come from R. Okay, for all I. But now let each alpha I to be written as ti plus ai such that 0 less than equals to ti less than 1, and these ais are coming from the integers. Why is it possible? It is possible exactly due to this thing which I mentioned previously, exactly due to this thing. Okay, I can write 0.10 plus 2 to be equal to 2.10. So this is your element ti, this is the integer part, and this is exactly the real coefficient. Clear? This is what I am exactly doing. So I am just removing the integer parts from the coefficients. That is exactly the thing I am doing here, because these ti's will constitute the coefficients of an element inside the fundamental domain, and these ais will be constituting the elements coming from the lattice. Because then I can write w as, so if I just distribute this out, so I get elements of the form t1 v1 plus t2 v2 and so on till tn vn. So this will be one part of the element, another part will be a1 v1 plus a2 v2 and so on till an vn. And clearly if you observe that this is an element, as I just said, this is an element in the fundamental domain, because the coefficients are less than 0 less than equals to ti less than 1, and this element, because all these coefficients are integers, so this is in L, and this was exactly what we required. What more we require is sort of uniqueness, that this representation is in fact unique. Okay, so suppose I can write w as say t plus v, which can be represented as t prime plus v prime, be two distinct representations. Such that t and t prime they come from capital T, and v prime they come from L. Okay, yeah, this will do. So now then, by the previous proof, that how the proof of the representation that this representation actually exists. So we have that then t1 plus a1 times v1 and so on and so forth till tn plus an times vn. This must be equals to t1 prime plus a1 prime till, okay, I should talk about here. So w is in the form t plus v, yeah, okay, so yeah, it will do. So this is your so t1 v1 plus till tn vn constitutes the part t, and a1 v1 till an vn constitutes the part v. Similarly on the right hand side, t1 prime v1 till tn prime vn, it constitutes the part t prime, and a1 prime v1 till an prime vn constitutes the part v prime. Okay, so till what I have is tn prime plus an prime till vn, right? But all these vi's are linearly independent, right? Since these vi's are linearly independent, therefore each of these coefficients must be equal to each other. Therefore ti plus ai must be equals to ti prime plus ai prime for all I belonging to block n, that is I equals to 1 2 till n. Okay, so this implies that ti minus ti prime is equals to ai prime minus ai, and this is an element from the integers. Okay, but to observe that, but these elements ti and ti prime are in the range 0 to 1, and they in fact need that their difference needs to be integers. But for their difference to be an integer, it must be exactly equal to 0. Their difference must be exactly equal to 0. This implies that ti minus ti prime must be exactly equals to 0, or implies ti must be equals to ti prime. But if ti equals to ti prime, then that immediately implies that t is equals to t prime. But if t is equals to t prime, that will immediately imply that v, which is w minus t, it is same as w minus t prime, which is equals to v prime, and which means that this representation is in fact unique, right? Okay, so that's all for this lecture. In the next lecture, we will come up with the concepts of quotient torus, and after studying quotient torus, we will be talking about the Minkowski's theorem. So meet you guys in the next lecture.